I figured I'd cover this subject since somebody was talking to me the other day. About 7 or 8 years ago, a group of us started talking about analog computers again. Everybody started getting really quiet. A lot of people got really, really quiet really fast. These are people who are usually chattering about certain subjects within computer science that are computationally intensive, and the reason why they got extremely quiet is because analog computers actually do these types of computations rather quickly. In fact, it's the most efficient way of doing it. The problem is the output is difficult to attenuate for it because analog computers are rather difficult to program for. But if you understand how to attenuate and how to program for an analog computer, the output is much faster and more efficient and way, 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 way less expensive than the more computationally intensive digital system. They lack in the capability of being generally reprogrammable and reconfigurable, though, which is, that's another benefit from digital systems that we have. And I'm covering this subject because I thought it was important just to remind everyone that the only reason we use digital systems today was the fact that the legwork of developing a programming method and a instruction set had already been done by a woman named Ada Lovelace back in the 1800s, prior to any of this other stuff. Otherwise, they probably would have, done the hard, arduous work of doing the hardest and most difficult task of building an analog computer that could do this one simple task, and that would be operate with a low noise coefficient. Digital systems are absolutely privileged in the fact that they have a zero tolerance for noise coefficient. What this means is there's no noise, because it's either turned on or it's turned off. If it has a issue of bit flipping or a high error content, you can filter for it, you can program for it, and you can correct for it. You can CRC, you can ECC, you can do numerous methodologies or techniques and programming techniques to remove error from the output of your computation. No matter what you try to do, you can just simply ignore the error in hardware, in operating system, in API, or in actual software. You can ignore the error. So there are 3 levels of being able to ignore the error and multitudes of other checks and balances to get rid of the error. That's the primary benefit of digital systems, and that's why digital systems are actually the dominant systems on the planet. Not because they're generally reconfigurable, it's because you can remove the errors. That's the only reason. There are very few reasons for you to be upset the fact that you can remove errors from digital systems. In an analog system, if you have an error, it can take your otherwise computationally cost-effective system and turn it very expensive very quickly, because it can cause a storage issue, a buffer overrun issue, cause a crash, it can corrupt your data. There's a lot of things that it could do, which is why these days mixed mode systems are kind of important, because we use analog systems as well as digital systems in everything. All digital systems these days have an analog component. Just most people aren't aware of it. Most people don't know which part it is. The digital switching system is built on the power supply system, or rather the power supply circuitry, is actually built on top of an analog system. It's triggered by voltage, constraints and limitations. So if the analog system hits a certain voltage, it cuts down, and it's controlled by an analog system, basically. And that's basically all circuitry is power systems. That's all it is. Like digital circuitry, that's all a digital system is which way is electricity going. That's all it is. There are no super secret tricks or anything to it. It's just which direction is the voltage going, which route is it going to get there, how much resistance is it going to meet or match to on its way through that system. That's all it does. But going back to the conversation that I had with this person a few years ago, analog systems are much quicker at specifically designed circuits in the fact that they don't have to worry about switching time. They're essentially instantaneous. As fast as electricity can flow through this wiring, or the circuitry, it's as fast as it can go. In a digital system, if you have interrupts and other things you have to program for, and you have micro opcode that has to control which circuits are doing what at what time, you have timing constraints and slew rates. While you do have slew rates in analog system, the computational output is instantaneous, basically. In a digital system, the slew rate can cause timing errors between your RAM or your memory and your computational pipeline or your advanced circuitry if you have to pull it out and do a double adder or something like that. You have to run it through a multiplexer or a multiplier circuit or do differentiation of some sort using multiple mass circuits built or etched into the hardware or software or whatever it is. Clearly, it depends on the complexity of the calculation and computation you're doing. But an analog circuit can be designed just to do that one specific computation, and it does it almost instantaneously. And it adds noise to some degree. If you can reduce the noise down to almost nothing or have a percentage of variability, the more complex your circuit is, the more average noise they assume you're going to have, the greater the variability at the end of the computational cycle. And that's what they call noise, is how much of a variability you're going to have. It can be eliminated by doing other things, designing the circuit to be a little more complex, which is stuff we understand now. Like, we understood it back then, like not we as in me and you, or you and I. We as in people who were designing those systems back then. My grandfather was included in those circuits. He worked on some of that stuff as well. Large analog computers that ran many different things, including automation within a factory in the 1950s and 60s. Things that most people aren't even aware were going on back then. Some manufacturers had automated analog systems. But the whole point of this conversation is the fact that don't assume that Python is it. Don't assume that what's already there is it. If you can do calculus, you understand trigonometry, you can probably figure out what kind of architecture you need to build something without having to buy a GPU and do it without it. I'm not going to tell you anything else. If you can't figure it out from there, then you probably should not be involved in machine learning. You probably shouldn't be, because these systems have existed for decades. This is nothing new. We've been doing this stuff for a long time. Just nobody talks about it.